Hello everyone, welcome to today's Yebo Physics session. Apologies for the late start. We are just going to continue from where we left in the previous week, and we are still looking at units and measurement, and for today we will proceed also into vectors. So I'm sure you have seen, even with your practicals, the importance of significant figures and decimal places when dealing with measurable quantities. So we'll not delve much into that. I'm sure you saw a number of application questions that relate to the addition, subtraction, multiplication, and division of different quantities, and how you deal with these significant figures in the different cases. So for those joined on Teams, I hope you can see my screen. I'm sharing a screen on Teams, and for those joined on YouTube, I'm sure you can receive the stream without buffering. So if you cannot hear me, please indicate so that we don't, for the sake of recording, so that we don't go through the stuff that we're covering without the audio. So we'd want you to hear everything, or want you to benefit for those also that are not joined as yet. If they will see the recording, they should be able to hear what was happening through this session. So our first question will be on from the PHYV set of questions. So I'm gonna share that question screen shortly. Okay. Right. So the question goes, a position time graph for a particle moving along the x-axis is shown in figure P2.7. So we have the figure down here, figure P2.7. So it shows position versus time. So this is just given as position time graph, and it's along the x-axis. That makes it a displacement. So it's a displacement time graph. Find the average velocity in the time interval t equals to 1,5 seconds to t equals to 4 seconds. So from t equals to 1,5, which is the, to t equals to 4 seconds, what will be the average velocity? So in this case, for average velocity, we will take the covered distance over the time. So that will be from the covered displacement over the time, which in this case at t equals to 1,5. So find the average velocity. So we'll call it v. Average will be equal to x final minus x initial over delta t. So the final x, the value of x final is 2. I'm sure it's the displacement ends at 2 meters when we are 4 seconds through the motion, and the initial value of x at 1,5 is 8, and the time there is between 1,5 and 4, so delta t is 4 minus 1,5. Yes, Ntando, you are welcome. Thank you for joining. Kindly confirm if you can receive the audio and see the screen that I'm sharing at the moment. So looking at question number 1 of TAT practice question, the set of TAT practice questions, which is TAT 2 from your PHYV 101 module site. So you can refer to that one if ever you want to check something from the site. So for this first question, we have been asked to find the average velocity in the time interval between t equals to 1,5 seconds and t equals to 4 seconds. So at t equals to 1,5 seconds, we said we'll get average velocity by simply finding the displacement total displacement over the change in time. So the change in the displacement during that time is x final minus x initial along the x, and the final is 2, the initial being 8, that is at 1,5, the value of x is 8. And the time taken there is 4 minus 1,5. So this is negative 6 over 2.5, which is 24 over 10. So this should give us minus 2.4 meters per second, where the negative sign implies that this is in the opposite or negative x direction. So the average velocity is minus 2.4 meters per second in the negative. Okay, it's minus 2.4 meters per second or 2.4 meters per second in the negative x direction. So this is the velocity. Average velocity is still a vector. Take note, is still a vector. The second part goes determine the instantaneous velocity at t equals to 2 seconds by measuring the slope of the tangent line shown in the graph. Okay, so gradient of a displacement time graph gives you the velocity. So in this case, since it's not a uniform velocity throughout, the tangent to the velocity at a point gives us the instantaneous velocity. So this instantaneous velocity is given by the tangent at t equals to 2. So we go to t equals to 2, which is here, and the line has already been drawn for us. So we would we will then have to calculate the increase in y over increase in x. So instantaneous velocity is equal to the gradient. Okay, so this is instantaneous, and the gradient is delta y over delta x, which is simply y2 minus y1, or y final minus initial, whatever we consider as the final and the initial, over the x final minus x initial. In this case, okay. So the y in this case, the y is represented by x, and the x-axis has got delta t. So we can change there to say x final minus x initial for the gradient over t final minus t initial. So it's because the x-axis we have t, in the y-axis we have x. So don't worry about that issue of x's, but you just have to know what quantity you are dealing with there. So this is still displacement over time to give us velocity. So that's consistent. So x final, we'll say that's 0. No, we're not ending at 0. Okay, for the gradient. So for the gradient, we'll go up to that point. So we'll consider that point. X final for the gradient 0. X initial. So we'll consider in this, which point can we read here? So let's take which is the best point we can take there. Okay. So if we take this point here, this will be, I think we can safely say that's 9.5. That's 9.5. So x initial is 9.5 minus 9.5. So you have to choose any point that you want, any readable point that gives you a good estimate. So the t final is at 3.5. So t final coincides or corresponds to x final. So that's 3.5 there. 3.5 minus x initial will be 1, minus 1. So that's negative 9.5 over 2.5. And you can calculate that. Let's see what that gives us. 9.5 over 2.5. Negative 9.5 over 2.5. Minus 3.8. So we get negative 3.8 meters per second for the instantaneous meters per second. It's also in the negative direction. V instantaneous at, or we can call it V at t equals to 2. We can call it V at t equals to 2 like that. V when t equals to 2. That's instantaneous velocity. So we have a 3.8 there. Then our next question says, what value, at what value of t is the velocity 0? So the velocity is change in displacement over time, and the change, when the change is 0, then also velocity is 0, and this is the turning point where the gradient is 0. So this is when x is equal to 2, or when t is equal to 4. So the value of t is what is required. So at t equals to 4 seconds. So we say at t equals to 4 seconds, then v equals to 0 meters per second. Okay. Great. So that's how we deal with graphs. There are answers 2.4 minus 3.8 and 4 seconds. Then question number 2. Question number 2. If you have a question, guys, feel free to just unmute yourself and give us your contribution, or just ask the question that you have, or you can give a comment, or just interact with us. We would love that very much. Okay. So we proceed. A truck covers 40 meters in 8.5 seconds. So we have a truck. We'll call our this distance, we can call it S or X. So let's use X equals to 40 meters. So X is quite deceiving though, because you always think it's simply a horizontal X direction. But anyway, for a truck, it's usually horizontal. The path, we'll just assume it's horizontal. So if it is 40 meters, that's our X. We can use S there to just show its displacement. Then the time given is 8.50 seconds, while smoothly slowing down to a final speed, V final, of 2.8 meters per second. So this is the given information in this question. What is the original speed? And what is the acceleration? So given those variables, the displacement, the time, and the final speed after that time, what is the original speed? So in this case, you can use an equation that takes into account your final speed and gives you the original speed, which is Vi, unknown. V initial is not known. And you also incorporate time and displacement. So which means we have, from our list, V final equals to V initial plus A t. We also have V final squared equals to V initial squared plus 2A x. So x is generally x final minus x initial. So you can have that as x final minus x initial. In this case, we've just been given that as x. We've been given that. So that's the displacement usually. That's the displacement. You can call it dx. And this will be dt. So those symbols, if you want, you can just incorporate them, if that's the way you can understand it better, to show that it's a change. It's a change in the time. It's not just an instantaneous time. So that will give you like show that you have in-depth understanding of what's happening. Okay. Then we have one which says, okay, delta x in this case is Vi times delta t plus half a delta t squared. Okay, so now which one do we use? Which of the equations do we use? We want to find Vi. We want to find Vi. So we don't have a. It means in this case, we need to choose the most appropriate equation so that we find acceleration and we find the original speed. So what do you say we do? So we have another one, the fourth one, an interesting one, which says that average velocity. So average velocity will be x delta x over delta t is equal to Vi plus Vf over 2. In other words, delta x will be Vi plus Vf over 2 times t. So in this case, this is the best equation to use. This is the best equation to use. It simplifies everything and takes into account the acceleration. And now that we are not given acceleration and we are given the t, then we can find only one unknown, which is the Vi. Our single unknown Vi can be found. So I've listed 4 equations here. This being the first, equation 1, equation 2, for final velocity in terms of initial velocity and displacement. And we have equation 3, which is the displacement in terms of the initial velocity and time when acceleration is also given. And equation 4, which is the average velocity equation. So this is the one that is the best to use. You could you could use in this case 2 equations, the first one 1 and 3, to eliminate maybe acceleration and then find since delta t is given, and then find Vi remains as the only unknown. So 2 equations can also help you solve for 2 unknowns. But let's just use, I know you guys would want something that just gets you to the point. But what is important is understanding. You should understand what it is you are doing. And now that we have delta x, we can substitute. We have 40. And delta t is 8.5 meters and seconds is equal to the Vi is the initial, which we want to find, plus the final velocity 2.80 meters per second, everything over 2. So we eliminate by multiplying by 2 both sides. And what we have is 80.0 over meters per second over 8.5 minus 2.80 meters per second equals to Vi. So 80 over 8.5 gives us 9.411. Subtract. So this part will give you 9.411, and you subtract 2.8. You remain with 6.611 meters per second equals to your Vi. This is the original speed. So this becomes the original speed of the truck. And now its acceleration, we go back to equation 1, this one. We have the final speed of 2.80 is equal to the initial speed, I got 6.611. Initial speed plus A times delta t, where delta t is 8.5 seconds. So A is our only unknown in this expression. Then we can do what we know best to find our A. 2.8 minus 6.611 over 8.5 equals to A. So this is making A the subject. That shouldn't be difficult. Please use your calculator also and see if we get to the same answer. 2.8 minus 6.611. Everything is divided by 8.5. Minus 0.448 minus 0.448 meters per second squared equals to the acceleration. The truck is slowing down, so it's decelerating. So this is the acceleration. It's a negative. So because the truck is slowing down, we get those two answers. Okay. So we are given the initial speed, the final speed, which is in the direction of motion, is positive. So our initial is still positive. So the directions are such that the acceleration is opposite to the direction of the velocity or of motion. It's a deceleration. All right. An inquisitive physics student. This is question number 3. An inquisitive physics student and mountain climber climbs a 50 meters high cliff that overhangs a calm pool of water. He throws 2 stones vertically downward, 1 second apart, and observes that they cause a single splash, meaning they arrive at the surface of the pool at the same time. The first stone has an initial speed of 2 meters per second. How long after release of the first stone do the 2 stones hit the water? So the first stone is thrown and it takes has an initial speed of 2 meters per second and goes through 50 meters. So we need to see what's the expression to use there. Right, so we have height, or do we call it y? Let's call it height or y. Climbs high cliff. So let's use y. In this case, equals to 50.0 meters. Right, then they cause a single splash. The initial speed, so for stone 1, V initial for stone 1 is equal to 2 meters per second. We don't know what V final is, and we don't know what the initial speed of the other stone is. But we know that T initial T2 initial minus T1 initial is equal to 1 second. T2 is the time when the second stone is thrown. So this time is a second later. So T2 will be greater than T1 by 1 second. Okay. Now the question is, how long after release of the first stone do the 2 stones hit the water? So how much a time does the first stone take to reach the ground? So we have G equals to 9.80 meters per second squared. So this is the information that we have. So with initial velocity, displacement, we have initial velocity, displacement, and G. Which equation do we use? Here is our list of equation. So we have acceleration, displacement, and initial velocity, something like this. So we can use an equation like that. Displacement is there, initial velocity given, and the time is what we need to find. Acceleration we know. So in this case, our expression will be delta y is equal to v initial for 1 delta t plus half. So I'm considering downward direction as positive. Remember, so delta y will be positive, v1 will be positive, g will also be positive. Half g delta t squared. So this is the equation. Delta x equals to v1 delta t plus half at squared. So that's the same equation. This time we are dealing with the y vertical direction. So now, since y is 50 meters above the ground, we substitute vi 2.00, delta t is what we need to find, plus half 9.8 times delta t squared. So this is a quadratic equation. This is a quadratic equation with this coefficient as your a, this coefficient as your b, and that coefficient as your minus c. When we take it to the other side, it becomes c. So it means in this case it's in terms of it's quadratic in terms of delta t. So for us to get delta t will be equal to minus b plus or minus, remember the quadratic formula, the root of b squared minus 4ac all over 2a. So we substitute the coefficients. Minus b is minus 2 plus or minus the root of b squared, which is 4 minus 4 times a is half of 9.8, 4.9, 4a times c will be negative 50. Minus c is 50, so c is negative 50. All over 2 times 4.9. So you have that expression, delta t, the time. So let's see, minus 2 and minus, so the most appropriate answer there will be when we are considering the positive part of that rooted term. So we have minus 2 plus the square root of 4, that's plus 200 times 4.9. Divided by 2 by 4.9, which is 9.8. So this is 2.9968, 2.9968 seconds, which is 3 seconds. So we're given the least significant figure there is one significant figure in terms of both time and velocity. So to one significant figure, that becomes just 3 seconds. So we just have 3 seconds there. So if our time is 3 seconds, this is how long after release the first stone, the release of the first stone, when the 2 stones will hit the water. This is 3 seconds after the 2 stones are the first stone is released. So the two stones hit the water 3 seconds after the first stone is released. Then what initial velocity must the second stone have if the two stones are to hit the water simultaneously? So this is now a relationship question where the second stone is thrown a second later. So which means its time, the time of its trajectory is a second less than t. You remember this expression? T2 initial minus T1 initial. So if T1 initial is our reference point, which is the 0 seconds, so this one is launched 1 second into the motion. And they both reach the water 3 seconds into the motion. It means the time taken by stone 2 is 3 minus 1. So that's 2 seconds. It takes 2 seconds in its flight. So take note, the reference when first stone is thrown is when t is 0. Then at t equals to 1, the second stone is thrown. And at 3 seconds, both reach the surface of the water. So the time for T2 will be from the first second to the third second, which is 2 seconds. And now this can help us find the initial velocity of the second stone. The initial velocity of the second stone. It still travels through 50 meters. So we have displacement. We don't know final velocity, but we have displacement, we have time, and acceleration. So we use the same equation. We just go to the same equation, which we said is delta y is equal to v1. This is stone 2. Delta y is the same. v2I times delta t plus half gt squared. Take note, we said the downward direction is positive in this case. So delta t squared. So since delta t equals to 2, the time of flight for stone 2 is equal to 2. So we have 50 equals to v2 initial times 2 plus half 9,8 times 2 squared, which is 4. And this will just give us 2 there. Then 9.8 by 2, 50 minus 9.8 by 2, 19.6, I think, minus 19.6 over 2 equals to v2I. So 50 minus 19.6, 30.4. So 30.4 over 2. 15.2 meters per second is the initial velocity of the second stone. And what is the speed of each stone at the instant the two stones hit the water? So this is the final velocity for each stone, and we know that v1 final equals to v1 initial plus at. So this v1 initial, we say it is 2 plus 9.8 times 3, 2 plus 9.8 times 3, that's 31,4 for v1 initial for stone 1. v1 final, and v2 final will be v2 initial plus at, where t2 is equal to 2. So that's 15.2 meters per second, which we found now, plus 9.8 times 2. So 15.2 plus 9.8 by 2. So that's 34.8 meters per second, V2 final. So those are the velocities of the stones whereas they hit the surface of the water. Okay, so guys, the rest of the questions will continue. We're gonna be experiencing load shedding in a minute. So we'll continue with the rest of the questions in our slot tomorrow. We have another slot running between 12 and 2, depending on the load shedding schedule. So we'll always be adjusting these times, but we'll make sure all your questions are answered and all the tutorials will be conducted so that you can see either the recordings depending on your availability. So otherwise from me, it's bye-bye for now. Let's meet again tomorrow.